All right. Hi, guys. We're going to go ahead and jump into our Chapter 7 lecture. So let me go ahead and pull up our PowerPoint for that. Okay, there we go. So here we are getting into theoretical distributions. And this is going to be really important for our inferential statistics. So if you remember our first lecture of the quarter, we talked about inferential and descriptive statistics. So what we've talked about mostly in this class so far has been descriptive statistics, the ones that describe a set of data. However, inferential statistics, which we start jumping into today, make inferences about a set of data. They take information about a sample and make inferences about a population. So we're going to begin to dip our toe in that pond today. So we're going to be talking about the normal distribution, so I thought that was cute. So here is a very important distinction that our book makes at the beginning of the chapter. So we have empirical distributions and we have theoretical distributions. So empirical distributions, this first one here, our scores come from actual data that we gather from our participants. So the distribution that we derive from that data comes from actual data. It comes from a real place, from data we actually collected. So it's basically the real stuff that we get from the sample. Theoretical distribution, on the other hand, is a hypothesized distribution that and the scores are based on mathematical formulas and logic. So this one is a mathematically derived distribution that does not use actual data to do it. So it's used a lot in statistics to determine probabilities. So we use these theoretical distributions to determine probabilities of events occurring. When our theoretical and empirical distributions have a correspondence, so when these two things overlap, we can then arrive at probabilities about future events occurring. So the big example of this that we will see in this chapter is when our empirical distribution is a normal distribution. It's normally distributed. So if we've got an empirical distribution from our data, and it's normally distributed, that's kind of wonky, but that's okay, we can see that. So this is the data that we get from our survey or whatever study that we're doing. We can then compare that to a theoretical distribution. And then we can make inferences about our sample because we have that theoretical distribution to go off of. So we can make inferences and arrive at probabilities because we have this correspondence between our empirical and theoretical distribution. So we're going to be talking about three different types of distributions in this chapter. The normal distribution, like I've already been talking about and that we've talked about a little bit in this quarter. And we're also going to talk about that rectangular distribution and the binomial distribution, which we haven't talked too much about. So here are some examples of those things. Rectangular distribution is where in the data set we have the same frequency of every data point, so it levels off like a rectangle. Normal distribution is a lovely bell curve. And a binomial distribution is where we have a distribution of basically only one of two events or only one of two things can occur. So like a coin toss, we can either have a heads or a tails. So that's talking about events where there are only two possible outcomes. That's what a binomial distribution is. Okay, so this chapter talks a whole lot about probability and how we can derive probabilities when we have our overlap of theoretical and empirical distributions. So let's talk a little bit about probability, how it works, and all that good stuff. So one very important thing to keep in mind is that probability ranges from 0, which is no possibility of event occurring, and 1, there is 100% certainty that an event will occur. So our values range from 0 to 1. So it cannot occur, certain to occur. So we can have values between this range. You can also think of this as failure and success. So probability of 0, it's going to fail to occur. Probability of 1, it will succeed. You can also denote probabilities in a ratio form or a percentage form or a decimal form. So a lot of different ways that you can convert that 0 to 1 range. So the ratio of successes when we're writing a probability in ratio fraction form, you do success or probability of So when you're writing a probability in a ratio form, you put the probability of that event occurring, that success happening, over your total probability amount. So an example of that, like I have here in the slide, so success over total probability. So an example of this would be a deck of cards. So say that we wanted to know the probability of picking an ace out of a 52 card deck. So there are 4 aces in a 52 card deck. So you would put 4, because there are 4 aces, our total number of aces in a deck, over 52, because that is how many cards we have in the deck. You can then convert that fraction into a decimal, which is 0.077. So we have a 0.077 chance of drawing an ace out of a 52 card deck. And then you can also convert that to a percent. So 0.077 becomes 7.7%. So you can write it as a percent, you can write it as a decimal, and you can write it as a fraction. So those are the different ways to denote probability. Clear all drawings. There we go. Let's move on to the next slide. So probability is expressed as chances, like chances in 100. So again, we're getting that percentage feel here. So let's go back to our ACE example. We had a 0.077 chance of getting an ace out of a 52 card deck. You can also express that in a percentage like I have here. You have a 7.7% chance out of 100 that we will pick an ace. So you can express probability in those 3 different ways. You can also add up probabilities as well. So if I wanted to see what the probability of picking an ace and a king out of the deck, I could simply add up the probabilities. So we have 4 aces in a deck. We also have 4 kings in a deck. The probabilities associated with those is 0.077 for each. So then we just add up those probabilities and we get 0.154, or 15.4% chance of either drawing a king or an ace. So if you added up all individual cards, you would eventually get 1. And this makes sense, right? Because we get our probability ranges from 0 to 1, or from 0% to 100%. So some other examples here with the deck of cards. So say you wanted to look at what the probability of getting a face card is. There are 4 face cards in a given suit. So say we wanted to look at face cards in the hearts suit. There are 4 face cards in the heart suit. So that's 4 out of 52. Again, we get that same 0.077 probability, or 7.7%. Say I wanted to look at choosing a certain suit, what the probability of getting a card in the heart suit, for example. There are 13 hearts in a deck, so 13 out of 52 is a 0.25% chance, or a quarter chance, or 25% chance of getting a heart. Half of the deck, so say what is the probability of getting a black card, a black suit? That is 26 out of 52, or a 50% chance. So you can express it in all those different ways. Binomial distribution. So like I was saying earlier, with the binomial distribution, this is a distribution of events that can have only 2 possible outcomes. So you either have a yes or a no, or a heads or a tails, on or off, that sort of thing. So binomial only has 2 outcomes that can occur. So the biggest example that our book uses and that I'm going to use to kind of practice with is coin tosses. So here we have events of 3 coin tosses sequentially done. So we have a first toss, a second toss, and a third toss. And here are all the different outcomes you can have. Heads, 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 tails, and so on and so forth. So I'm going to do some examples with that in a minute to kind of show you how to derive probabilities from that. So here is an example to kind of get you going with the probability. So here we've got 2 tosses happening, first toss, second toss. We start out with 100% chance of probability. We break that in half, as we see here. Then we break that half in half. So this tells us that the probability of getting heads and then heads is 1/4 or 25%. The probability of getting heads then tails is 1/4 or 25%, and so on and so forth. So we break down that probability at each coin toss. So if we look at this theoretical distribution of outcomes, we see that each occurrence has a 0.125 chance of happening, or alternatively 8 out of 100. So that's 12.5% when we flip the coin 3 times. So you have a 12.5, what this is saying is you have a 12.5% chance of getting heads, heads, heads when you flip the coin 3 times. You have a 12.5% chance of getting heads, heads, tails when you flip the coin 3 times. And I'm going to draw that out and show you why that is. So let me, we're going to pause our screen share there for a minute and just go to our full board. Let's get this back. Okay. Okay, so when we are doing this binomial distribution, we can have only one of 2 events occur, one of 2 possible things happen. So with the coin toss, we can have either heads happen or tails happen. So remember that probability ranges from 0 to 1 or 0 to 100%. So we start out with 100%, and then we divide that in half. So 50% chance we're going to get tails. 50% chance we're going to get heads. So that's our first toss. That's our probability for our first toss. Then we have our second toss. Then we're going to break that down even further. Again, we can only have a heads or a tails. Here, heads and tails as well. So we've got our second toss. We break this 0.5 into half again because we have our binomial distribution. We can only have one of 2 things happen. So when we break 0.5 in half, we get 0.25. 0.25. So you have a 25% chance of getting heads and then tails when you flip your coin twice. You have a 25% chance of getting heads and then heads when you flip your coin 2 times. Likewise, you have the same thing happening here when you have tails happening first. So when we've got tails and then heads, 0.25% chance, or I'm sorry, 25% chance, not 0.25. So we have 25% chance of getting tails then heads, 25% chance of getting tails then tails. So that's your second toss. Now we're going to complicate things and toss the coin 3 times. Third toss. Again, heads, tails, we can only have those 2 outcomes. We're going to break this 0.25 in half. And when you do that, you get 0.125.